Hello everyone, this is Spencer Snowling from Hydromantis, and I'd like to welcome you to today's webinar where we will be talking about temperature effects in GPSX. However, I would like to, if you can indulge me for a brief moment, let you know that we have, since our last webinar, celebrated our 30th anniversary here at Hydromantis. So I would like to give you a little bit of a background and celebrate our anniversary by showing you a little bit of the history of GPSX and of Hydromantis. As you may know, the company was started here in Hamilton, Ontario by a couple of individuals out of McMaster University, Dr. Gilles Patry and Dr. Pierre Cote. And in the beginning, GPSX was sort of a research project into being able to model activated sludge processes using the IWA type models. And this was the oldest image of GPSX that I have been able to dig up while I've been here at Hydromantis. This is actually a prototype for the interface when it was running on a Unix workstation. And we can see here that it had the drawing board and the splitters and combiners and the individual unit processes and the controls for running simulations and so on. And this was running in X Windows. Back in the day when we required running it on a Unix workstation due to the heavy computational component that was required. But eventually it went on to become a commercial product. This is version 2.2. This is the first version that I became familiar with when I was a graduate student. And I remember back in the day, GPSX was delivered on these big tape data cartridges. And I still have one of these here in my office. You'll note that this giant piece of equipment here, which weighed about 4 or 5 pounds, only holds 150 meg. But that was the way that GPSX was shipped around. I think back at the time, Hydromantis used to sell the software and the hardware together. And you can see here it's a different interface at that time. But then when I joined the company in 1999, this was version 3, and we moved to improve the interface over time, so much more sort of conventional drawing board with some sort of flatter objects. But we started to introduce more simulation types, bar graphs, and so on. And it was in 2002, version 4, which we first moved completely out and away from the Unix type environment, and it was running fully on a Microsoft platform. And we can see here we adopted a different type of drawing board, still some sort of flat icons that we were showing, and other types of tools that were there. The simulation control panel was in itself its own separate window that popped out. And we developed it up and improved it over time. Version 5 was actually a very big step when we moved away from the old methodology of setting up graphs where you had to do a setup of a graph and define which variables you wanted on it and then show that graph and so on, into a much more drag and drop type approach here. And then version 6, which was back in 2010, was the next big step where we went to a much improved system to be able to display the information with the quick control panels and so on. And this was also the step where we introduced the Mantis 2 biological model, which was the one that now is the full plant comprehensive model with pH and so on. And it has continued to be the focus of our development since that time. And of course, the most recent version, as you know it, is version 6.4. And it's the one here with Sankey diagrams and statistical analysis and state point diagrams and so on. So these are all things that are part of the GPSX product as we have continued to develop that over time. We, of course, have other products that we have developed at that time, too, during the history of Hydromantis. ToxChem for air emissions, CapDetWorks, which is our costing tool, and WattPro, which is our drinking water simulator, and so on. And so on behalf of myself and my colleagues here at Hydromantis, I would like to thank you all, our clients, for a really wonderful 30 years. I've had a very lovely career here at Hydromantis, and I thank you for being part of that. So on to the webinar. We're going to be talking today about how temperature effects are modeled in GPSX and part of the activated sludge models. So, I should introduce myself once again. Spencer Snowling. I'm Vice President of Product Development here at Hydromantis, and I'm the caretaker of GPSX, as you probably know. And the agenda for today is to talk about the temperature settings. We have a couple different ways that temperature is set in the software. And then there are a number of different effects that temperature has on the output of the system. And it actually has far-reaching relationships into the biological parts, the physical parts, and the chemical parts of the activated sludge process. And I'm going to cover all three of those today. And as always, I like to run a desktop example where I will do that, and then I'll answer any questions that you have at the end of the webinar. So type those into your GoToWebinar question board as you see it as part of your dashboard there, and then I'll save those up and then I'll answer them at the end. Okay. So there are two sets of temperature settings in GPSX. The global one, that is the global setting of temperature that is for the entire plant, and the local. So the global one, the global setting is for plant-wide temperature, and you can get at that on the plant-wide properties button, which is found here, this little red dot button at the top toolbar. Now, this is actually something that is new in version 6.4 of GPSX, but we've collected up a lot of the plant-wide settings and put them here and accessible from that button. The global temperature is the one that's applied to all of the units, unless it is overridden by a local temperature. The local settings for each individual object allow you to override the settings for that object. So if you have one unit that is, say, indoors or something, so that it is at a different temperature than all of the other ones, you can go to the physical menu. So right-click on the object, go to Input Parameters and Physical, and then click on this More button down here. And then you will get the local environment selection menu. And so you can see up here at the top that will be off by default, but if you click it on, then you'll see some settings that become available to you that are for this unit specifically, including the liquid temperature and the air temperature and elevation above sea level. I'm not sure that would be different for any particular unit process, but also standard air conditions, where you can override our typical air with units if you wanted to do high purity oxygen, for example. So the liquid temperature is used for most of the adjustments that we'll be discussing today, the biological and chemical adjustments, and also the inlet air temperature is the one that is used for making adjustments to do with aeration. So let's start with, of the three things, let's start with the biological temperature effects. And the one main thing, this is the one that is sort of the most significant temperature effect in activated sludge models, is the effect of the biological kinetic constants. So most of the parameters that you see on the kinetic menu are adjusted for temperature using the Arrhenius equation. Not all of them, but most of them, particularly the growth rates and the death rates. And that is done using an equation that looks like this. We take the temperature setting for 20 degrees Celsius, and then we multiply by this temperature parameter that is taken to the power of T minus 20, where T is the temperature in Celsius. So this allows for an increase when you have something that is above 20 degrees Celsius, and a decrease when you go below 20 degrees Celsius. So the parameters that you see on the kinetic menu when you right-click on the object and select Input Parameters and then the kinetic menu, these are the settings for 20 degrees Celsius. And these are the ones that will then subsequently get adjusted before being used in the equations. The temperature kinetics, the ones that tell us how sensitive those parameters are to temperature, which is the theta value in the Arrhenius equation that I showed you earlier. These are found at the very bottom of that kinetic menu. So the variables for 20 degrees are at the top. These variables will be found down here at the bottom, and they're shown by their their cryptic variable name. And so this temperature kinetic coefficient here for MUH, the heterotrophic growth rate, is 1.072. It's usually a number that's slightly bigger than 1. So when you take a power of it a few times for a few degrees, we will see that exponential type of increase. So we can see here the MUH is for the heterotrophs and MUA is for the autotrophs. This is the set for the mantis model. So let's take a look at the Mantis 2 model, where we actually have two-step nitrification, and we also have heterotrophic growth. And in our two-step nitrification, we have AOBs and NOBs. This is ammonia oxidizing biomass and nitrite oxidizing biomass. And we can see that as we increase the temperature here from 10 degrees Celsius up to 30 degrees Celsius, that these things increase on an exponential function, as it has been applied by the Arrhenius equation. So we can see here that these, of course, increase, and there's a very interesting effect, actually, that happens with the NOBs and the AOBs. They have not only a different kinetic value. At the lower temperatures here, the AOBs have a slightly lower growth rate than the NOBs do. That makes some sense, of course, because you don't want the second step in the process to be the slower one, or otherwise you end up with the accumulation of nitrite in the middle. However, when you get up to the higher temperatures here, you can see that they each have their own individual value, but their own individual sensitivity, their own temperature coefficients. So the NOBs, or the AOBs, pardon me, increase faster, and eventually it flips over the other way around once you get up here about 28 degrees Celsius. So here, this is looking at just the heterotrophs. Here we're looking at growth rate versus death rate. And you can see that they both, of course, are adjusted for temperature, but the growth rate is affected quite a bit more than the death rate is. So both of these things will be changed when we go to different temperatures in GPSX, and you'll be able to you'll be able to see the effects in the change in the mixed liquor and the change in the amount of treatment that's happening. And of course, you can actually use the GPSX sensitivity analyzer to see this very nicely. You can go right to doing tutorial 7, except change influent flow rate to temperature, and then you can see this type of relationship here with effluent ammonia versus temperature. And you can see that, of course, at the very high temperatures, we're getting full nitrification, so we're having low ammonia. But once we get down to the lower temperatures, where things have been adjusted for that colder liquid, we can see that, of course, the growth rate is backed off, and then at some point we lose nitrification down here just below 10 degrees Celsius. Okay, so that's the biological one. So all of the biomass types have at least some temperature correction built into them. So in the Mantis 2 model, where there's 10 biomass types, they all have their own coefficients, and you can find that at the bottom of the kinetic menu. On to physical temperature effects, and most of this is really about aeration. So the aeration system is sensitive to temperature in a couple of different ways. One of them is the solubility of the oxygen in water, and the other one is the mass transfer coefficient, KLA. Both of these are corrected for temperature all the time in GPSX. So if we're looking at, first of all, in a aeration model, this is the equation, this is the derivative for oxygen in the model. The amount of oxygen changed in that tank over time is the amount of oxygen coming in minus the amount going out, plus the amount that's being introduced by the aeration system, and then there's a term here on the end for the biological reaction. So right now we're interested in talking about this physical part, which is the mass transfer coefficient times the oxygen saturation concentration minus the concentration that's in the reactor at a given time. So if this is much lower than the saturation, then you'll have a bigger driving force moving forward. So this CSAT value here, the concentration of oxygen at saturation, is something that is corrected for by temperature. And we calculate that here with this equation. We start with a known value of the oxygen saturation concentration at standard conditions at 20 degrees Celsius, for example. Then we correct for temperature, we correct for beta, this is your sort of salts and other things that are in the wastewater, and then alpha, of course, which is the, this is delta here, which is the pressure correction, and that is for correcting for depth within the tank, but also the barometric pressure, so that is affected by the elevation of above sea level, and that's where that parameter comes into effect here as well. So we're looking at temperature correction, and we take this number basically from a lookup table. It's not a mathematical relationship as much as an interpolation off of clean water data that we got from the EPA design manual. So You'll find that as we adjust for temperature, that oxygen saturation is automatically adjusted, and also the oxygen transfer is adjusted as well. Here we take the standard value for 20 degrees Celsius, and then we correct it for temperature, for fouling, and then for the general wastewater alpha value, right? So this temperature part, it's actually the same type of mathematical equation as the Arrhenius equation for biology. And we adjust that again so that it is a function of going above or below 20 degrees Celsius. And again, it's that exponential kind of curve. So at colder liquid temperatures, as we go down into the colder temperatures, the oxygen saturation concentration goes up, but the mass transfer coefficient goes down. So that allows you to sort of store more oxygen in there, but of course it takes more effort to make that, to get that oxygen transfer in there. There are a few other aspects of the aeration model that are also sensitive to temperature, and you can actually look in our GPSX technical reference to get all of the details there. Particularly the things like the density of air and the density of water, those things are corrected for temperature as well. They're not very strong effects, but they are somewhat there. Okay, lastly, we'll move on to the chemical part, and specifically here we're talking about the pH model. So as you know, in GPSX, in the Mantis 2 model only, we do a full pH balance across the entire plant. And some of that pH model is sensitive to temperature. So I've put up this very simple carbonate system here where we have the dissociation of carbonic acid here. And you can see these pK values. Those are the ones where that is the value of the dissociation constant. And that's the point at which we move and we lose one of those protons moving over here. And there's two of them in the carbonate system here, one around 6.3 and one around 10.3. These values of pK1 and pK2, those acid dissociation constants are actually sensitive to temperature. And so here's a relationship. I scanned this right out of my favorite geochemistry textbook this morning and put that here, and you can see how these things, acid dissociation constant pK1 and pK2 are sensitive with temperature. And so as we go to higher temperatures, the values of those go down. So that can have an effect on what's going to happen with the pH calculation, and that can therefore have an effect on how much CO3 2- is available that can be used for precipitating out other things. So these are all they're not hugely strong effects, but they are there and they are present in the model, and we do make those temperature corrections appropriately. Okay, so let's take a look at a desktop demonstration here so that we can see this a little more clearly. So I've set up this layout here. This is actually the nitrifying plant example off of our sample layouts menu. And you can see here, this is just a conventional plant with activated sludge. We're doing fully aerated. It's got a DO controller on it set to 2 milligrams per liter. So it's going to supply enough air to do that job. And then what I'm going to do is run a sensitivity analysis on temperature. So I'm using the GPSX analyzer function, which is found up here, and I'm going to adjust liquid temperature from 5 degrees Celsius up to 35, which is a fairly extreme ranges there, but let's just do that so that we can illustrate our point. And I've plotted a number of things that are functions of the equations that I've been showing you earlier. So I'm going to turn that on. And I'm going to let this run. And we're going to do this just for steady state. So it's going to solve a steady state solution for all 1 degree at a time as it moves up here. You can see this here. This is increasing the temperature and finding a steady state solution and plotting the concentrations and so on versus temperature. So we can see here, first of all, that not surprisingly, the effluent quality gets better as the temperature gets warmer. So of course we're getting a little bit better treatment, a little bit warmer, a little bit more biological activity. So the things like the effluent COD and the effluent TKN, they go down as temperature goes up. So let's take a look at the three elements that we mentioned earlier, the biological part, the physical part, and the chemical part that are all tied together in GPSX for activated sludge modeling. And we can see here, first of all, that for the growth rates, those biological ones are adjusted as we discussed earlier. So basically, this is a recreation of the diagram that I showed you earlier, but we can see here how the heterotrophic growth rate is adjusted over time, the temperature corrected heterotrophic growth rate as these go up with the increasing temperature. Okay, so we'll move on to the aeration section now, and what I'm showing here is the oxygen saturation in black, and so we can see that goes down as we get to warmer temperatures. As I mentioned before, you can have a higher oxygen concentration at the much lower temperature, so way down below 10 degrees Celsius. Here we're up around 12 milligrams per liter, and at the very high temperatures we get down below 9 down to about 7.5 or about 8 milligrams per liter down here. This blue line is actually the actual oxygen transfer rate as we go up higher. So that is a function of several things, the amount of loading into the plant and the temperature and so on. So, but we can see here that in general, as we got more higher temperatures come along, we get more treatment and we get more, in general, more oxygen required to do that biological demand. Okay, and lastly, we'll take a look at these temperature-corrected dissociation constants. And we can see here, it's a very flat line, meaning it's not very heavily corrected. So these two ones in black and in red here, those are the carbonate dissociation constants, and they go down a little bit as temperature goes up. And here's the pH in blue. Of course, it's not affected greatly by the by these temperature corrections, but of course it is also a function of the amount of ammonia coming in and so on too. So anyway, those are there, and we can see those effects. So as I illustrated here with the sensitivity analysis, there's a lot of moving parts. A lot of things are affected by temperatures to greater or lesser degrees, but we can see that they do have an effect on the overall performance. And that is all tied together to give us an overall effect of temperature on activated sludge. Okay, a few final thoughts here. There are a few other places where we've done something special with temperature correction. There is one unit process that extends the temperature model to much higher temperatures, and that is the open basin high purity oxygen model. And that one has its own temperature model. You can actually do a little bit of prediction of temperature with this one. But because it has a very potentially high oxygen feed temperature, it has a different Arrhenius relationship. So below 35 degrees Celsius, it's basically the one that we've talked about before. But then it gets to that point where it's being inhibited. So in the other side, above 35, it starts to go down again because the temperature is undergoing, the biomass is undergoing temperature inhibition. And so that's just a quick highlight to show you there that at the very high temperatures, you can see that effect here. There are a few things that people have asked me over the years how we correct for temperature, and I've just listed a few things that aren't adjusted for temperature, that we don't have any correction for. So the settling parameters in and of themselves are not changed for temperature. It's something that I think we would like to include in some way, but there is no nicely well accepted model that relates temperature to the types of settling parameters that we use in GPSX. The biofilm parameters, again, the parameter itself, attachment and detachment parameters, for example, are not adjusted for temperature. Of course, the growth is, so the amount of detachment that you get is a function of growth, and that is adjusted by temperature. And then the energy calculations, again, the calculation itself is not a function of temperature, but of course the demand will, the biological activity usually drives the demand, which will therefore derive the, a change in energy calculation, the amount of energy used. So, and a way to sum that up is to say most of these things are indirectly dependent on temperature, but not adjusted particularly directly. So, a few final thoughts here. The temperature is one of the most important settings in an activated sludge model. It's important to make sure that you adjust those site properties there. It's connected to many of the processes that are going on in GPSX, and it's important to make sure that you come here and set that global temperature or the local one if you're using that. I know that I have personally gotten tripped up on that a few times along the way, where I've had trouble calibrating a model, and then found that of course it was because I hadn't come here and set the temperature properly.